I think we'll have the math meeting in the, not in the conference room, somewhere else, somewhere bigger.
Why?
So, all right, I will begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class and this opportunity we have to meet and to study your creations. Pray that you be glorified in what we do, Lord. In your name I pray there, Jesus. Amen. All right, so I still don't have like an example that's what I want yet to illustrate integration of forms over boundaries and so forth, but I think a good part of the homework that I've assigned you, you should be able to make sense of, because it's essentially the kind of integration that you've done before, just in a different notation, right? It's curves, it's surfaces, it's volumes. So the problem of orienting the boundary doesn't really appear much. I did find one small calculation to share with you that I think is kind of neat. And I think it may actually answer the question, but it doesn't answer the question in a way that I'm terribly happy about. But let's see here. So if I look at the square rectangle with sides vertices P0, P1, P2, P3. The thing I was trying to do yesterday that I just couldn't think of is to say that this rectangle is actually the sum of two simplices, namely P0, P1, P2, plus P0, P2, P3. Right? So it's like, that's the thing I wasn't thinking of, is like, I could write a rectangle as what? Oh. What is wrong with this? Anyway, don't be so surprised. Let's see here. So the boundary bar is, P1, P2 minus P0, P2 plus P0, P1 plus P2, P3 minus P0, P3 plus P0, P2. And if you look at that, and what you're left with is exactly what you kind of expect, right? Like, if I just make one more step, right? Right, that is exactly this. It's the counterclockwise oriented proper boundary of the rectangle, since I built it as the sum of two properly oriented simplices. What? Oh, okay, that was a tracing. So anyway, one of the things I suggested is like one way we could derive orientations of boundaries of the manifold we're integrating over is if we had a triangulation of the manifold, we could just differentiate. We could take the boundary operator of the triangulation, and that would reveal to us the boundaries. And I do think that's true, but I also think as a calculational method, it's quite horrible. Because the next thing I thought about was, oh, okay, what about a cube? So how do you write a cube as a union of tetrahedra? So how many do you guys think it would take?
Tetrahedron?
4? I have a vote for 4. At least I hear at least 12. Very good. Yeah, 12 regular tetrahedra will do it. That's true. That's good. So my son, I asked him yesterday, and after about 10 minutes with modeling clay, he produced the answer of 5. That's true. That's the smallest number of irregular tetrahedra, which can be used to fill out a cube. The disturbing thing was this morning at breakfast, I asked my wife how many tetrahedra does it take to fill out a cube? And she looked for about 1.5 seconds and said 5, which was disturbing to me. And then she said, it's obvious, and made fun of us for not knowing it.
Show and tell.
Anyway, I still don't see the 5, but anyway. I mean, I sort of saw it when I saw the clay, but whatever. So my larger point is that doesn't seem to me like a very good method of calculation, since it's that hard to do the cube, right? And it's fairly obvious what the boundary of the cube is. It's like the outward oriented faces, right? So anyway, I'm just telling you I'm still working on hopefully a reasonable method of calculation, but I don't have it yet.
I don't know, it didn't seem that hard to your wife.
That's right, yeah. So the method of calculation is find my wife, ask her to triangulate your space, and then go from there, I guess. Yeah, that's good. Yeah. So my wife is pretty awesome. It's true. All right. So anyway, let us go on. So today I'm going to talk to you guys about electromagnetism in differential form. I heard a mixture of oh and ugh, which is what I expect from math majors. You guys were so gleeful when we cut Physics 232 out of the required course list for math majors. Obviously a mistake. But what I want to talk about today is electromagnetism in terms of differential forms. So I guess I probably owe you guys a brief synopsis of like what is electromagnetism, you know? It's the study of electric and magnetic fields, right? And so the principal aim of electromagnetism is to study Maxwell's equations and understand them. Maxwell's equations are the equations which govern the electric and magnetic fields. So we use E is the electric field. B is the magnetic field. These are both functions on R4, which we're going to use t, x, y, z coordinates for. Right? So they're functions on time space. I can usually say space time, but I think it's time space. Time went first, you know. I don't know, but space time sounds way cooler though. So that's what we say. Space time. All right. Anyway, you know, I'm starting to get annoyed with the state of my markers. Like I'm out of decent markers. I really hope this one works. Anyway, these have to satisfy Maxwell's equations. So Maxwell's equations state that the divergence of the electric field is equal to rho over epsilon naught, and the divergence of the magnetic field is equal to 0. The curl of the electric field is minus partial B partial T, and the curl of the magnetic field is mu naught times the current density plus epsilon naught times partial E partial T. Right? The names of these equations respectively are Gauss's law, no magnetic monopoles, this is Faraday's law, and this guy is Ampere's law with Maxwell's correction. Maxwell's correction was important because it sealed the deal in terms of predicting radio waves and so forth. This right here is Maxwell's correction, that term. That has to do with the displacement current, which is a necessary modification outside the context of magnetostatics. Magnetostatics being the case that you have long steady currents. Now I guess that begs the question, what on earth else is going on here, right? these a bunch of letters. So mu naught and epsilon naught constants. These are constants, right? Mu naught is the permeability of space. And this is the permittivity of space. I probably misspelled them, who cares? And it turns out that C is equal to 1 over the square root of mu naught epsilon naught. This is the speed of light. And what else should I tell you? Oh, what is rho and what's J? That's kind of important. So here, rho is equal to, let me write it over here. Rats, I don't know where I'll put it. Rho is dq dv. It is the charge per unit volume, the charge density. Q is charge, like electric charge. J is equal to the current density. So in particular, you would probably haven't looked at, well, I don't know. If we take the surface integral of J through a surface, that calculates the current flowing through the surface. So like the current, usually use I for that. I is the integral of J dot ds, let's say, over some surface. Through some, that's the current that flows through surface, right? Right. Okay, so that, in a nutshell, these are Maxwell's equations, all right? And physicists probably spend, I don't know, 6 courses or something studying these, something like that. The elementary course, the junior level course, it's second semester, a semester of optics, a semester, and then maybe 2 semesters of like graduate electromagnetism. That would be something like that. 5 or 6 courses, I guess. All right, so there's, of course, like a lot goes into these, but what I want to talk about today is how we can reformulate these in terms of differential forms on time space. And so to do that, we need to talk a little bit about Hodge duality in time space, but I think I will put that off. I guess I can't. All right. So how does Hodge duality go? So like it turns out that the Hodge dual of dx is minus dy, wedge dz, wedge dt. The like the Hodge dual of dy and the Hodge dual of dz, those are going to be minus dz, wedge dx, wedge dt, and this one's going to be minus dx, wedge dy, wedge dt, because I did. And let's see here. What else? The Hodge dual of dt is equal to minus dx, wedge dy, wedge dz. According to I'm using the conventions that are in chapter 9 of my notes, all right? Which, as I have told you, are off by a sign relative to Rentelin's conventions. I think his Hodge dual is minus my Hodge dual. All right. Now, all right, so what else? That's the Hodge dual for the 1 forms. The Hodge dual for the 2 forms, if we have dt, wedge dx, that Hodge dual is 2 minus dy, wedge dz. If we have the Hodge dual of dt, wedge dy, and the Hodge dual of dt, wedge dz, you can guess what those are. We've got minus dz, wedge dx, and minus dx wedge dy. All right. Sorry, I'm trying to find. I should not have deleted. I used to have a table in here of all my Hodge duals, right? And I sent you guys that in an announcement, but I don't currently have it printed out, which is really annoying. Because I'd just like to write those down for our reference for this lecture. You know? All right, so what's the Hodge dual of dx wedge dy? What's the Hodge dual of d y wedge dz? What's the Hodge dual of dz wedge dx, right? Yeah, but the fact that the Hodge dual is, so that's the thing is, like Hodge dual of Hodge dual isn't necessarily 1 in the Minkowski metric. So it's not involutive. It may be -1. I don't remember is the thing. What's that? The Hodge dual was -1 for Minkowski.
Well, it depends on the dt.
All right. So give me a second.
Violet has the spreadsheet up.
Yeah, the 2015.
Yeah, Hodge dual is 1. Always. According to the table.
Are you looking at the right space? I think it says it in the paragraph above the table.
The paragraph above the table, my current notes.
In 2015. I'm not sure.
I don't know what's happening in here. Some kind of nonsense. Let's see here. Mike Wazowski. Oh my goodness. Oh my goodness gracious. All right, I have found it. It's in my 2011 notes. Yay! Oh man. Oh, that's just the basis. That's not the Hodge dual.
Wikipedia has it.
Yes, but that's nice, but it doesn't matter because I need the convention. It's convention dependent. Okay, so.
It's either this or it's the opposite.
Well, yes, I mean, I know what it is up to a sign. I mean, that much I know. But minus dz wedge dt minus dx wedge dt. All right, minus dy wedge dt. All right, great. Now we've got it. Okay. Anyway, all of this to say, if we take a typical, what's a one form look like in it looks something like alpha equals to, let's say, alpha naught plus, for lack of imagination, ADX plus BDY plus CDZ, right? Which we could express as alpha naught plus the work form corresponding to the vector ABC. And yes, there's a dt there. Thank you. So I just want to, what's the Hodge dual of this then? So we got minus dx wedge, good grief, alpha naught, right? Dx wedge dy wedge dz minus, thank you. And then when we Hodge dual this, of course, that's going to give us like minus the flux form of ABC wedge dt, yeah? And that's a 3 form, right? And that makes sense because the Hodge dual of a 1 form should be a 3 form because we're working 4 dimensions, 4 minus 1 is 3, right? Now, a 2 form we can write as something like, I don't know, gamma, and we can write it as, let's say, something of the form, I guess I don't know, I'm lack inspiration here. dt wedged with adx plus bdy plus cdz plus, you know, like a flux form, right? Plus a flux form of, let's say, vector, I don't know, I need some more letters here, d, e, f, all right? In other words, an arbitrary 2 form we could express as equal to, like, you know, dt wedged the work form of a vector field ABC plus the flux form of a different vector field DEF, right? So a 2 form corresponds to not 1 vector field, but 2 3-dimensional vector fields, right? We need 2 3-dimensional vector fields to describe a 2 form here, right? And while we're at it, what's the Hodge dual? Using linearity and the basic rules over here.
Negative a dy dz, well, which
Well, no, I want, in terms of the flux form.
negative flux of ABC.
Okay. And see down here? So when we take the Hodge dual of the flux form, it flips us over to minus the work form of DEF wedge dt. Now, of course, we can use the antisymmetry of the wedge product to get rid of, like, we could put the dt first and make it a plus. You know, there's different things we could do. I just wanted to point out that this is what happens. So this is, you know, Hodge dual. It takes 2 form to 2 form in 4 dimensions, right? And then, let's see here. What about, well, I guess there's still like the Hodge dual of the 3 form and, excuse me, the Hodge dual of the 1 form and the 4 form, but let's skip those. All right. Next up, let's talk about exterior derivatives, right? Let's talk a little bit about exterior derivatives because we'll need these. What is it? And so I'm basically going through one of the homework problems you guys already worked out, right? So d alpha for that 1 form, how's that work? We end up with the work form of the gradient of alpha naught wedged with dt. Plus, you know, man, I need a different let me call this vector here like f, if you don't mind. Oh, f's a bad choice. G vector. So when I differentiate that, I get what? I get like, so like this is true because I only have the, there's no time derivative. There's a time derivative in the differential of alpha naught, but that wedge with dt wedge with dt is 0. Yep.
Write down work form and flux form.
Well, the work form of the vector field G would be like G1 dx plus G2. I'm only working with like the 3-dimensional ones. I'm not doing anything. I may have talked to you about a 4-dimensional one, like in a conversation, but here I just mean the 3-dimensional one. And the flux form of that same vector field is like G1 dy wedge dz plus G2 dz wedge dx plus G3 dx wedge dy. These are the usual 3-dimensional work form and flux form maps that we talked about. And so when we differentiate the omega sub g term, right, that gives us a curl, right? But it also gives us a time derivative. So we get like the flux form of the curl of g, yeah? And then, all right, so like in this, we also have like a, when we work it out, it's, oh, all right. I'm trying not to write it out as the thing. I do have time derivatives from the exterior derivative of the omega piece there. And I think what that is dt wedge the work form of the partial derivative of g with respect to t. So we can put these two things together, and it gives us the work form of the gradient of alpha naught minus the time derivative of the spatial part, wedged all of that wedged with dt, plus the flux form of the curl of g. So that's what it looks like, the exterior derivative of the one form. And that's what you guys derived in like problem 75, I think. Something like that. Was it, what was it, 45?
We're on the 60s right now.
60s? I don't remember. I have talked about this problem to several of you. I know. I have not written my solution yet myself, but I have talked about the solution with at least 2 or 3 of you. So, yeah. Okay, so what happens when we differentiated? Well, actually, let's just stop there. Let's do the rest of the derivatives when we come to them. All right, so sorry, I'm just trying to get the ball rolling here in terms of this is the exterior calculus. It involves both like partial derivatives of the vector fields that underlie the forms, as well as like curls and gradients of things, right? So, all right, so here we go. For current. This is a definition. J upper mu is a 4 vector. And by definition, it has 2 pieces, the charge density and the current density. If we lower the index with a Minkowski metric, we get a minus here and a J here. So this is using the eta minus 1, 1, 1, 1. So when we lower a temporal index, we pick up a minus. All right. So all of this said, we can define the current one form. So J equals to minus rho dt plus the flux form, not flux form, the work form of J. So this right here, this defines the current one form. But I mean, to be clear, it involves both. I mean, this simultaneously is folding in both the charge density and the current density. All right, as a one form in three. In space-time. Now, what's the Hodge dual of the current one form?
Minus rho dx, which is
Right. But because there's a minus is a plus, so we get rho dx wedge dy wedge dz, very good. Plus what? Or minus what? Mm-hmm. Minus the flux form of J. Wedge dt, right. So that's the Hodge dual of the current form. Now I mentioned this because we'll need this a little bit later, all right? All right. Next up, we need to define the four potential. The four potential, if we put an upper index, A upper mu, as a space-time vector, it would have components voltage and the vector potential. Now the vector potential is probably something you guys have not heard of before. I'll explain more what that means as we go on. Just take it from me here that V is the voltage, like, battery voltage, the voltage you've heard of and come into contact with. Hopefully not. Yeah, hopefully not, right? Well, you got struck by lightning once, right?
Not quite.
But
I was in the lake.
You
with
felt lightning.
The dog that had a chain collar on, and I saw lightning strike, and my body locked up.
I think that counts. I don't know.
Indirect strike.
Yeah, it
If
must
it
have.
didn't hit you and but it came through the water, that's probably it.
Yeah, and like everyone around me felt it too.
Yeah,
And we
so
got the heck out of the water.
Who's the dog, okay?
So if we
It was fine.
Oh, good.
Well, even when I did like a dog chain. Bless you.
What?
So if we lower the index on the 4 potential from a contravariant 4 vector to a covariant 4 vector, we get minus on the voltage. Again, because we're using the Minkowski metric. This corresponds, of course, to a current 1 form, which we can write as A is equal to minus V dt plus the work form of the vector potential A. So this right here is the potential 1 form, or sometimes you'll hear it called the 1 form potential. All right. And if we wanted to, we could calculate the Hodge dual of this. I don't know if it really matters or not, but the Hodge dual of A would be V dx wedge dy wedge dz minus the flux form of A wedge dt. Again, I don't really know if that matters or not, but yeah. So let me explain to you guys a little bit more what voltage and potential is before we go on, because I think otherwise it's just kind of like just esoteric nonsense, right? Well, I don't think this, whatever you're about to do, it's not going to fix it. But that may be true, but I'm going to try to make this understandable as much as is possible. So in electromagnetics, the electric field is minus the gradient of the voltage function. And the magnetic field is equal to the curl of the vector potential. This is how the potentials and the fields are related. That's not quite the whole story. There's more. See, because for the electric field, it also ties in. It also ties into the vector potential. In particular, and I'm a little rusty, I'm trying to find it. I'm not sure about the sign, you know. It's in here. I was just reading it. I know it's in here. See, this is why I need to teach electromagnetism. All right, it's on page 220 of my notes, but minus the gradient of the voltage, minus the time derivative of, so it's minus partial A, partial T. This is the terms with the vector potential. This is news. Even to those of you who've taken Physics 232, you've not seen this vector potential, right? Even if you took Physics 232 with me, even I'm not so crazy as to teach you the vector potential in Physics 232, right? This is something that is the province of junior level electromagnetism, all right? But that's it. So what this means, right, is if you give me the voltage function and you give me the vector potential, I can calculate what the electric and magnetic fields are from those by these derivatives, right? Now they're not unique because, of course, whenever you differentiate stuff, you lose track of a certain, amount of data, right? So there's freedom here called gauge freedom. It actually there's a freedom up to like a function of space and time. Derivatives of a function of space and time can be like you could. Of course, you can shift the voltage by adding a constant, and you can actually check it out. So like if we had A prime is equal to A plus like nabla lambda, then when you calculate the curl of A prime, what happens? What's the curl of a gradient? Are we over here? Okay, cool. This, search your heart and realize this is 0. Which means that A prime and A both would calculate the same magnetic field. This is gauge freedom, your ability to switch the voltage by adding a constant, or also, maybe that's not quite enough. I guess I need that lambda has no time dependence as well, right? So if lambda has no time dependence, we're okay. Anyway, there's more to say there, but I'll stop there. So these are the potentials, all right? How about so I've showed you how we can implement, so let me keep track of what we're doing here. We're working our way towards explaining how to write down Maxwell's equations using differential forms. All right, that's our goal today, one of our goals. And so to do that, we need to have a way to implement the current density, the charge density, the current density, and also the electric and magnetic fields. All right, so what I'm telling you is the best way to understand electric and magnetic fields is with the potential formalism. So we're going to try to connect the potential formalism to the electric and magnetic field formalism, but we're also going to do that at the level of like exterior calculus. So there's like a couple different things going on here. But obviously the next thing we need in order to make good on this in these connections is I need to come up with some kind of like differential form which encodes the electric and magnetic fields, right? Notice that these equations say that the electric and magnetic fields are linked, right? That means they're part of the same object. What object has 6 degrees of freedom that we could use here? A 2 form, right. So we're going to use the 2 form to put the electric and magnetic fields together into an electromagnetic field tensor called the Faraday tensor. So here's that. F is equal to the work form of the electric field, wedge dt, plus the flux form of the magnetic field. That's the Faraday tensor. Now, we can write that in the repeated index notation as 1/2 F mu nu dx mu wedge dx nu. U, take your U back. This is one of the most beautiful things I will write this semester. So you got minus E1, minus E2, minus E3 up here. E1, E2, E3. Zeros down the diagonal, of course, because it's an antisymmetric matrix. And I mean, a 2 by 2 antisymmetric matrix corresponds, of course, to a, that was a 3. A 2 form. All right, there you go. This is the Faraday tensor. All right. If we were to take the Hodge dual of this thing, what would happen? Hodge dual of F is what? It works out to the flux form of the electric field minus the work form of the magnetic field, wedge dt. And so what that means, if you think about it, in terms of the matrix of components, it means that the electric and the magnetics are like flipped. But not exactly that. See, what happens is everywhere I have an E up here, right, I have like a minus B in this. So it would be like the components of the Hodge dual of the Faraday tensor would be like B1, B2, B3, minus B1, minus B2, minus B3. And the flux form, well, that's the same. So this is literally E3 minus E2, E1 in the dual tensor. But if you understand the pattern going from here to here, you can, bogart that pattern and go from, correspondingly. But, all right. All right, well, I think we have almost all the toys we need. We can start to play here in a minute. So one of the very, very central theorems of electromagnetism is the conservation of charge. All right? Conservation of charge says that if you look at some particular region, the change in the charge density there has to be directly related to the flow of charge out of there, right? If the density is decreasing, there must be an outward flow of current. If there's an inward flow of current, the density must be increasing, right? If we calculate the exterior derivative of the Hodge dual of J, what do we get? Let me try to find a better spot to work. I hate to erase the middle board, but I probably should. Oh, yeah, sorry.
Erase Sam's triangulation.
No, Sam's fine. I'll be up here.
It's just the third.
Okay, so the Hodge dual of J, we take the exterior derivative of that. We're calculating the exterior derivative of what was it? Oh man, I should wear my glasses. Haha. Oh, so rho dx wedge dy wedge dz. And what was the other piece?
Negative lux J.
Minus phi j wedge dt. All right, great. So let's think about how these exterior derivatives go. It's pretty simple. We got partial rho, partial t. dt, wedge dx, wedge dy, wedge dz. And that's all she wrote for the first term because any of the spatial derivatives are going to double up the differentials and wedge to 0, right? So only the time derivative matters there. And how about here? So check it out. We're going to have like partial j1, partial x dx, wedge dy, wedge dz, wedge dt, minus partial j2, partial y, dy, wedge dz, wedge dx, wedge dt, minus partial j3, partial z, dz, wedge dx, wedge dy, wedge dt. Reason being, all the other derivatives are 0 because there's a repeated differential otherwise. So yeah, I mean, in principle, there's 16 possible terms from the, the total differentials of functions of spacetime, but of those 16 possible terms, only 4 survive. And all the 4 of those survive with the top form, plus or minus, right? Like this dt wedge d, see that? But notice that this guy, and this guy, and this guy, they've got dt last, right? But notice that we got dx wedge dy wedge dz. This one, we can move the dx 2 spots over and get dx wedge dy wedge dz wedge dt. This one, we can move the z 2 spots over and get dx wedge dy wedge dz dt. So in short, it's all a plus. So we get partial rho, partial t, plus, well, let me get straight to the point. That's the divergence of j. dt, wedge dx, wedge dy, wedge dz.
You usually call that capital omega. Or not capital omega, just omega, like the top form.
Oh, yeah, I've got no special name for it, but yeah. I mean, it might be capital. I don't have a name for it, actually, no. I do call it the top form. Fair enough, you got me. I have no name for the top form. Yeah, that's perhaps a self-defeating statement. Yeah, fair enough. So, are you debating whether or not that's funny?
I just laugh.
There is nothing that you cannot complain about. Like it is, I cannot invent something. So theorem, the exterior derivative of the Hodge dual of J is equal to 0 is interchangeable with this equal to 0. But this is literally local conservation of charge. All right. So if we want to understand the conservation of charge in differential form notation, we should hope that the exterior derivative of the Hodge dual of the one current is 0. I'm just switching formalism so far, right? But what's about to happen is interesting, though. So what happens if we calculate the exterior derivative of the one-form potential? What's dA? So we're talking about the exterior derivative of minus v dt
Plus work.
plus the flux form of a vector, right? Excuse me, work form of a. My bad. So sorry. All right. Now we calculated the exterior derivative of a one form earlier today. And we have that boxed equation in the middle, right? So let's put that into practice now. It's allegedly equal to the work form of minus the gradient of the temporal component, which in this case is v, right? It wasn't minus over there, it's plus, but the minus is because there's a minus here. And then minus the time derivative of the spatial part, which in this case is a. That's my work form. And that gets wedged with dt. And then plus the flux form of the curl of the spatial vector, in this case A. Vector, also known as the vector potential. But I told you guys, for the voltage and the vector potential, these are related to the electric and magnetic fields in a very particular way. Look over there at how they were defined. We had that the electric field was minus the gradient of the voltage, minus the time partial derivative of the vector potential. And we had that the magnetic field was exactly the curl of the vector potential. This is nothing more than the work form of the electric field, wedge dt, plus the flux form of the magnetic field. But what's the Faraday tensor? What was the Faraday tensor? Over here, it is the work form of the electric field, wedge dt, plus the flux form of the... Hey, that's the Faraday tensor. Aha! This is equal to the Faraday tensor, right? So what does this mean in terms of the mathematics we've covered this semester? Theorem F equals to dA, so F is exact. But by the way, it's also closed, right? So dF is equal to d of dA, which is equal to 0. But what is dF equal to 0? All right. I'm a little scared to do it, but I'm going to erase the Hodge tools. Violet has them?
I'll take a picture.
All right. What is, I mean, okay, dF is equal to 0, right?
Yes.
But what does it mean, dF equal to 0? It's a level curve. You're evil. No. No. It means the exterior derivative of the work form of the electric field, wedge dt, right? Plus the exterior derivative of the flux form of B, right, is equal to 0. Did I do that calculation yet today? No, I don't think we differentiated the 2 form, did we? But that's what we need to do now. But you did work that out in the homework, didn't you? How's that work out? So if we think about it, we're going to have like 2 pieces essentially. We have the, we'll have dt wedge the work form of partial E, partial T. And then plus the flux form of the curl of E, wedge dt. And the differential of that one, I get the divergence of B, dx wedge dy wedge dz. But there's also a time derivative that I need to think about. Plus what? Plus, I guess it's dt wedge the flux form of partial B partial T, I think. Yeah? So I've got 0 is equal to the divergence of the magnetic field times the wedge of dx wedge y dz. And then I've got plus like dt wedge a work form, right? Oh, that can't be right. Just a second. Oh, yeah. I'm sorry. Okay, plus dt wedge. I got this. I'm sorry. I just need to collect my thoughts. I got this and that, right? Those can't be. Those something bogus here. It's not allowed. That's a.
Yeah.
This isn't allowed.
On the work form, yeah.
The work one by itself and the other two are
Oh, this is 0. That's not there. If I differentiate this with respect to time, I've got a dt. This is wedge with dt. This is dumb. Dumb. That's not even there. Idiot. Me, not you. So dt wedge the flux form of the curl of E. Why didn't it cost me a sign to move it to the other side? Phi is a 2 form. It commutes with dt. So I move the dt over here. And then I'm using the fact that it's an isomorphism, so I can bring that plus partial b partial t, like so. This is all equal to 0. Lo and behold, we have the divergence of the magnetic field is equal to 0, and that the curl of the electric field is equal to minus partial b partial t if you move it to the other side, right? In other words, we have just found what? This one and that one are in fact the same as this. So the two of Maxwell's equations just become the fact that the Faraday tensor is closed. Yeah.
Does it take a lot longer to prove that?
I don't know. I mean, depends on what the other ways are, I suppose. But now, the other two. So next up, we calculate the exterior derivative of the Hodge dual of f. All right. Next, let's calculate the exterior derivative of the Hodge dual of f. See what happens there. I think I'll just leave the boxed equation. Probably need that. But I think otherwise I'm probably okay. Almost certainly I will regret what I'm doing. At some point it's going to catch up with me, but it's okay. So how about the exterior derivative of the Hodge dual of the Faraday tensor? How's that work? So the exterior derivative of the flux form of E, right, minus the exterior derivative of the work form of B wedged dt. So we think through these, we get the divergence of the electric field, dx wedge dy wedge dz, plus the flux form of partial E partial t wedge dt, I believe. I mean, I guess technically it may be supposed to be the other way, but it's a 2 form, so it doesn't matter. And then the other term, hopefully I'll be less dumb this time, minus the flux form of the curl of B.